Okay, class, good morning. So again, this is the third presentation in this topic, so which is the vapor compression cycle. So by this time, class, I will give you an example of those who are discussed in this chapter. Okay. So here is now, class, the problem. So actually, this problem is a problem in our textbook. Uh, refrigeration or refrigeration and air conditioning by Santa Maria. Okay, so here is now, class. So a reverse Carnot cycle is used for refrigeration and rejects 1000 kilowatt of heat at 340 Kelvin. So while receiving heat at 250 Kelvin. So determine, okay, the coefficient of performance or COP, power required, and then refrigerating effect. Okay, so here is now, class, the T-is diagram of a reverse Carnot cycle. Okay, so actually, class, this is same as with the Carnot cycle, but the direction of the cycle here is against the direction in an actual Carnot cycle. Okay, so you will notice that one is here, so 2, 3, and 4. Okay, so here is now, class, the definition. So the Carnot cycle coefficient of performance is equivalent to the refrigerating effect divided by the work of compression. So actually, class, you can solve this using the temperature only. So the derived equation in our previous presentation is that the uh, refrigerating effect is equal to the change in entropy multiplied by the lower temperature or the cold temperature. And same as with here, multiplied by our Th minus T cold multiplied by delta S. So delta S now will be eliminated. Okay, so this is now a function only of T cold minus R over rather T high minus T cold. Take note, class, that the value here or the temperature should be in absolute. Okay, so the COP now is equals to 250, which is already given, divided by 340 minus 250. So the coefficient of performance now, class, is 2.778. Okay, so take note, class, that this COP is also related to EER or in energy efficiency ratio. Okay, so so we have here now the work. So actually, work is in Carnot cycle, that is QA minus QR, but here in the reverse Carnot cycle, that is QR minus QA. Okay, so substituting now here. So QR minus QR multiplied by T cold over T high. Okay, so or simply the equation of the work is equals to QR minus 1 or multiplied by 1 minus TC over T high. So actually, this was also derived from the basic equation of the uh, change in entropy here, class, is also eliminated. Okay, so the remaining now is QR multiplied by 1 minus TC over T high. Okay, substituting value now, class. So that is 1000. So this is the heat rejected multiplied by 1 minus the cold temperature is 250 and the higher temperature or the high temperature is 340. So the work now, class, is 264.7 kilowatts. And then solving now, class, the heat added. So that is QA or equals to 1000 minus 264 equals now to 735.3 kilowatts, class. Okay, so this is very easy. So another we have here. So in the next topic, so the refrigeration system or cycle or the vapor compression cycle. Okay. An ammonia vapor refrigeration cycle operates an evaporator temperature of negative 16. Okay. And a condensing temperature of 32. Okay. Determine the coefficient of performance. Okay. A. For an ideal saturation cycle. For wet compression with saturated vapor leaving the compressor. And see if the vapor at suction to the compressor is superheated at 6 degrees. Okay? So, here is now class the pH diagram. Okay? pH diagram of the for letter A requirements. Okay? So, take note that 1 to 2 is compression. So, take note that the assumption here is isentropic. And then 2 to 3 is constant pressure. And 3 to 4 is isenthalpic or constant enthalpy process. And another is constant pressure 4 to 1. Of course, at the evaporator. Okay? So, we have now here using the table, pH diagram. Okay? And the saturated table for ammonia. Okay? So, at state point 1, the temperature is negative 16. So, the corresponding pressure, of course, is 227.04. So, this is obtained from the table. And then, the enthalpy of the gas is 1,442.6 kilojoules per kilogram. So, state point 2, this is after compression. So, the temperature class is equals to 105 degrees. And then the pressure is 1,239.6. So the enthalpy is 1,690 kilojoules per kilogram. And at the end of or the enthalpy of the liquid at 32 degrees. Okay? So this is class at the evaporator. At the condenser temperature rather. Okay? So the pressure again is 1239.6 and the enthalpy of the liquid is 351.47. Okay? And at state point 4 class, so 3 to 4 is isenthalpic process. So but actually at 4 the temperature is negative 16. So and the pressure is 227.04 which is equal to the pressure at the suction of the compressor. And since it is isenthalpic, so the enthalpy is of course same as with the enthalpy at point 3, okay, which is 351.47. Okay, so again, computing now the refrigerating effect, the coefficient of performance rather, again that is refrigerating effect over work of compression. So, class, first you are going to familiarize how you are going to identify or determine the enthalpies and pressure at the saturation or saturated table and at the pH diagram. So, because class, if you do not master how to locate or identify the enthalpies, pressure, temperature, you cannot answer these questions below class. Okay? So, substituting the values now. So, from the identified given, so the COP now is 4.41 class. Okay? So, another, for the second condition, we have here, okay. So, for letter B. So, here is now class the values of the enthalpies. Okay. So, state point 1, 2, and 3. So, take note class, this is the the process where in solving problems, we always use this process. Okay. So the assumption, class, is the temperature at the end of compression, or the we usually use the condenser temperature, class. Okay? So at point 1, again, negative 16. At 2 is 32. This is, class, the condenser temperature. And 3, again, this is 32. And at 4, that is negative 16. You will notice, class, that we are going only to use two temperatures here. We are going to use the evaporator temperature and the condenser temperature. Okay, so getting now the pressure. So at 16,227, which is, this is already known. So in the previous slides, the enthalpy is 1288. Okay? I'm sorry. Okay. Total 7.04. Okay. And at 32, this is 1239, so already known. And the enthalpy is 1487.18. Same as for at the pressure at 3, same. And then 351.47. So, at 4, negative 16, already given, 351.47. And then, computing now for the COP. So, that is now equals to, substituting values, again, same formulas, okay? The value is 4.7. So, this is, class, quite higher than the COP obtained in the previous condition, okay? So, and the next condition, so we have here is 6 degrees superheat of the gas. Okay. So here is now, class, the pH diagram. Okay. So you will notice that at point 1, the horizontal line is extended. So beyond the saturation line here. Okay. Saturation line. So you will notice that it is located outside. So meaning superheated. Okay? So take note, class, that is superheated by 6 degrees. Okay? So getting now, class, the enthalpies. So at state points 1, 2, 3, 4. Again, instead of 16, uh, we deduct 6 degrees. So that is negative 10. So the value or the pressure is 227.04, and the enthalpy is 1456. So and then the enthalpy at the or after compression, class, is 113, and the enthalpy is 1239.6, and then enthalpy is 1713. Okay, at 3 is 32, and then the enthalpy is 351.47. Same pressure. Okay. And at negative 16, that is 225.1.47. So, COP now, class, substituting values, the value is 4.29, which is lower as compared to the previous values. Okay? So, it is 4.41, 4.7. Okay? So, here is, class, the value is 4.29. Okay, class, thank you very much. So, I hope you understand the example. Okay, so thank you very much, class.